Hi and welcome to the STOC talk about the paper Almost Linear Time Algorithms for Incremental Graphs, Cycle Detection, SCCs, ST Shortest Path, and Minimum Cost Flow. My name is Simon Meyerhans, and this is joint work with Li Chen, Rasmus King, Yang Liu, and Maximilian Probst-Gutenberg. We will jump right into one small part of the title called Incremental Cycle Detection. This is a very simple and well-studied problem where you're given a graph that receives directed edges over time. So one edge after the other arrives, and you should report the first cycle that appears. So here one might say that a cycle has appeared, but this I would not yet call a cycle, because the cycle has to also respect the directions of the edges. So this is finally a directed cycle, and here our algorithm or any incremental cycle detection algorithm can terminate and just return this cycle. Incremental cycle detection has been studied a lot over the last decades because of its applications to compiler design and die casting, among others. And I'll only compare with the previous state of the art for the sake of time in this talk. For evaluating the algorithms, the relevant parameters are usually m, which is the number of edges at the moment the cycle appears, and n, which is the total number of vertices. The algorithm by Bhattacharya and Kulkarni takes m 4/3 time in total to find the first such cycle. And the algorithm by Bender, Feynman, Gilbert, and Tarshan takes n² log n time to find the first cycle. And you see that the algorithm by Bender, Feynman, Gilbert, and Tarshan is better if m is roughly equal to n², which corresponds to the dense setting. And the algorithm by Bhattacharya and Kulkarni is better in the sparse setting. Finally, our algorithm runs in time almost linear in the number of edges, which is good in both the sparse and the dense setting, but we have quite large subpolynomial factors overhead. So for a very dense graph, actually Bender, Feynman, Gilbert, and Tarshan's algorithm is still faster. Our algorithm doesn't actually directly solve incremental cycle detection, but we solve the more general threshold min-cost flow problem. This problem is very powerful, and it captures not only cycle detections and strongly connected components, but also bipartite matching, approximate ST shortest path, approximate min-cost flow, all these types of problems that have received significant attention on incremental graphs before can be solved by reduction to threshold min-cost flow. So what is the threshold min-cost flow problem? You will see some similarities with incremental cycle detection, but it's going to be a bit harder to keep track of the parameters. So now the incremental directed graph G has two associated numbers with each edge. One of them will be a capacity, which you should think of as a positive integer. And what the other one will be a cost, which can be positive or negative. Then there's going to be a demand vector D, which encodes how much flow you want to send from one place to another, let's say, and a threshold value, large F. The goal of the algorithm is to report a flow f of cost at most large f the first time it exists, and this flow should not violate the capacities, and it should route the demands. I think it's easiest to focus on an example, so consider the small graph down at the bottom, where I set f to be equal to 3. All the edges are labeled with their cost and they have unit capacity. So you can just send one across the edge. And the demands will just encode that we want to send 2 units of flow from S to T. At moment 0, so at the start of the algorithm, it's not even possible to send 2 units of flow from S to T, so surely you can't do it with cost at most 3, which means that our algorithm doesn't have to return anything. Then at moment 1, a new edge is inserted, and now it's possible to route 2 units of demand from S to T, but the cost will be 7, which is too large. So our algorithm still doesn't do anything. Then at moment 2, second edge insertion, a flow of cost at most f exists, and at this point the algorithm will return this flow. Let's give you a small flavor about the algorithm and how it is internally working. Our threshold min cost flow problem algorithm first uses a reduction due to prior work by Van den Brand, Liu Sidford, and Chen, King, Liu, Peng, Probst, Gutenberg, Sachdeva from the threshold min cost flow problem to the dynamic min ratio cycle problem. Then we solve the dynamic min ratio cycle problem via an L1 oblivious routing that internally uses a sparse neighborhood cover. This just reduces the problem to the dynamic min ratio tree cycle problem, though, which is a more structured version of the dynamic min ratio cycle problem, which we then reduce back to the dynamic min ratio cycle problem by our core graphs. But this will yield a large size reduction, which means that this chicken and egg situation is resolved eventually. Let's first zoom into the dynamic min ratio cycle problem and define it and give some intuition about it. The dynamic min ratio cycle problem is again a problem on a directed graphs with lengths and gradients, where lengths are a bit like the capacities and gradients are a bit like the costs, in the sense that lengths are positive and gradients can be anything. The goal is now to find a circulation delta that minimizes the gradient divided by the length term. But now the circulation does not have to respect the direction of the edges. It's just the case that if you go against the direction of the edges, you flip the sign of the gradient term. So as a small example down below again, the length of this red cycle on the left is 4 because we just sum up all the length terms. And the gradient of this first edge here is -2. This edge here has a gradient of -1, but we traverse it in opposite direction, which means that it adds 1. And then this one, the last one, has a gradient of 1, but we traverse it in opposite direction, which means that we subtract 1. So the total gradient is -2, which means that this cycle achieves ratio -1/2. Brand-Liu Sidford showed that solving the subpolynomially approximate min ratio cycle problem in amortized time subpolynomial implies an almost linear time algorithm for threshold min cost flow. And we give such an algorithm that just solves the approximate min ratio cycle problem in amortized time subpolynomial against the general adversary. Notice that this problem was solved before in the famous max flow algorithm by Chen, King, Liu, Peng, Probst, Gutenberg, Sachdeva. But there, the authors used the structures of the update sequence to show that an algorithm that doesn't quite work against the general adversary suffices. But for the incremental problem, you really need it to work against the general adversary, because the increments can change the structure in a way that really seems to be mimicking a general adversary. So now that we know about the dynamic min ratio cycle problem, what is the dynamic min ratio tree cycle problem? Well, it's just that you're given a dynamic low depth tree and a dynamic set of off-tree query edges, and you have to report the min ratio cycle formed by a single query edge and the tree after every update. So what is this in this case? Well, there would be two query edges down here, and one of them forms the red cycle, the other one forms the blue cycle, and you can quite easily sum up the lengths and the gradients and see that the cycle 2 is much better than cycle 1 and achieves ratio even better than -1/2. Notice that this tree is structured and that the depth is very low and the lengths only increase over the height of the tree. This is no accident of this example. This is a general property that our dynamic min ratio tree cycle problem will have. How do we get this reduction from dynamic min ratio cycle to dynamic min ratio tree cycle? We do so via an L1 oblivious routing, which is a mapping that maps demand vectors to flows such that the total length is at most gamma times the optimum for every demand. So combinatorially, one can describe such an L1 oblivious routing as fixing a global root R and then map each vertex to a distribution of V to R paths, such that when you sum them up, you get a good cheap routing. So down below, you see an example where vertex 1 and vertex 2 both have some routing to the root R. And if you add these two flows up, you get the routing from vertex 2 to vertex 1 directly in this case. So a routing circulation will just be defined as an edge plus the routing of its endpoints. And we show that given a gamma approximate L1 oblivious routing, there exists a routing circulation that is a gamma approximate min ratio circulation. This means that a good L1 oblivious routing kind of contains the min ratio cycles. Since L1 oblivious routings are already tree-like in structure, it's not too big of a stretch to extract a tree from them. We do so via a dynamic sparse neighborhood cover, if that tells you anything. To go from dynamic min ratio tree cycle to dynamic min ratio cycle, again, we use core graphs, which are already crucial in the previous MaxFlow algorithms, that via a new spanner reduce the size of the problem quite a lot by contracting tree components, and then we just solve the dynamic min ratio cycle problem all over again. So to conclude, we solved the threshold min cost flow problem by reduction to dynamic min ratio cycle, and then via a chicken and egg problem with dynamic min ratio tree cycle and dynamic min ratio cycle, which yields the first almost linear time algorithm for threshold min cost flow. This then, by reduction, resolves a whole host of problems on incremental graphs, such as strongly connected components, ST shortest path, approximate incremental matching, where we improve the dependency on epsilon, and even more.